So this is lecture 35 on invariant maximality by Harvey Friedman. Please.
Thank you. So this is the last lecture I'm going to give on chapter 2, except I might say something about something that I haven't quite completed, but it's pretty uh, solidly close to completion, um, as I promised you. Uh, Anyways, you'll see what's uh, a little bit missing. So, anyways, this is the book again. This hasn't changed. These are and the idea is to move on to here. I don't know at this moment exactly what's going to be in here because I've been trying to focus on this. But this is some stronger statements that may involve, some of which involve logical notions, which are sort of powerful extensions that allow you to do more kinds of maximality, and I think this is worth doing. I mean, I might change my mind about this uh, if it isn't as extensive or powerful as I'm expecting. I might back off on this some, but the plan is to start on this chapter 3. This won't be anything of the size of this. It's more limited. If you remember, this is the old thing that hasn't been changed. It probably needs to be upgraded some, where I do local invariance. So all that stuff of 2025 most is pretty much well, except for the end of 2025, is this previous version of the book, so to speak. Before I came up with realized that there are these very clear, particularly end shift, clear notions of invariance um, that uh, that are directly mathematical, that should be featured um, before getting into uh, the stuff that's templated, so to speak, more of a templated thing, where you look at various things of certain forms. Anyways, so the hope is we start with this. I may pick up on something a little bit in here, but not much. I may talk a little bit about something left open, but basically we're going to move on to here, and then uh, this these things need fairly light changes in order to consolidate it with a new two. One doesn't want to repeat proofs completely. One can use some of the stuff in here, so to speak. Then we want to get back to the finite forms, which I started, and that has to be revisited very much. And then this is not clear what this is yet exactly. All right, so we're making progress. It's not going to take forever. All right, so uh, the changes here, not much changes. This is the same, namely there's nothing in here yet. All right, because I now have fixed the content of this pretty much, so I almost completely. So I'm ready to write the introduction. Um, yeah, I'm hoping to have a version of this next week on my downloadable manuscripts page, so it's all filled in with all the proofs, which are filled in on my own private copy, by the way. Largely, it needs some additions. Okay, so this is no different. This is no different. This is no different. Nothing new here. This is all stuff that's not independent. This is not different. I don't know whether I might have changed some expositional things, some minor expositional points in here, but there's no real change. Okay, then there's the proof that everything I'm talking about is equivalent to everything else. So there's all this equivalent stuff. Uh, going on here. And then we bring in this version, which is just on q to the k, but it's a kind of uniform form. This is nothing new, and I call it initialization. And it's equivalent to the other stuff. It's equivalent to the other stuff, but it's consolidated into q. Um, and this is no different. Okay, now here's where I actually did do the heavy lifting and actually fill in exactly how I do these proofs. And the idea is that I do it the same way. This thing is a thing unto itself because this is one dimensional, and that's just that's totally different. That's just flat out triviality. Here, I do it. This is really the guts of the thing. I do this where the combinatorics is just the combinatorics of omega 1. And so this is all in ZFC, actually in Z3 or whatever you want to, ZF minus power Z plus power Z of omega exists, that kind of thing. So this is understandable combinatorics of omega 1. And we try to, and it's done in 4 steps. And we try to prove it for arbitrary dimension k, now using a large cardinal, with the same proof structure. In other words, the only serious change is that the combinatorics in this part here, the combinatorics is of course more involved because it isn't even available in ZFC. It's large cardinal combinatorics as opposed to omega 1 combinatorics here. So I think it's a very good way to do this because people can read this. I'm talking about non-logicians can read this and think they understand everything and say, oh, well, there's something called large cardinal combinatorics going back to Erdős and his collaborators. And Friedman plugs that into this to the situation. And then Friedman proves, surprisingly, not in this chapter, in chapter 4, chapter, I used to be called 4. Now it's now it's 6. Friedman proves miraculously in chapter 6 that this Friedman proves in chapter 6 that these cardinals are needed to prove that. Okay, so and then I remark this is just 2 lines. I remark that when you fix k, you only need a k minus 2 subtle cardinal kappa. And that's actually implicit here because the large cardinal combinatorics I do here is based on k minus 2 subtle cardinal, where k is at least 3. In the case of k equals 1 and 2, dimension 1 and 2, these are already handled in the previous sections 2.7 and 2.8. Okay, so whoops, let's see. This stuff is not new from 2025. Some of it is not new. This general thing about what it means to be implicitly pi01 and what it means to be falsifiable and proof that they're almost the same notion. That's old. And now this is new. We apply to something that we did before. We show that all the statements except one are implicitly pi01 over WKL naught using Gödel's completeness theorem. And then we formally state our results, our positive results up here. We formally state them. Here we talk a little bit loose, using omega 1, using omega 1. Where's that? Using omega 1. This is a little bit vague by the standards of formal systems. It's not, and we just clean that up easily. Here it is. clean that up. Now, this is a new. I tried to work out the invariant maximality. So the invariant maximality officially is on the intervals minus n and closed. In addition to this uniform form with called initialization, which is on Q, but it's on minus n closed. And now the question is, if I have any other interval of rationals with real number endpoints, with extended real number endpoints, there's no extra work involved in bringing real numbers in there. But they're only the endpoints are real numbers or extended reals, not the elements. They're sets of rationals only. So I plan to completely analyze when this is true and when this is false in invariant maximality, no matter what the interval is, as long as it's got extended real endpoints and is a set of rationals. And I failed because there's one case that I haven't figured out. There's one case that I haven't figured out. Now you'll hear about it next week if I figure it out. But I figured it out I got everything except one thing. I solved completely what's going on. No, I'm sorry. I almost solved it completely what's going on here if the left endpoint is closed, is a left bracket and a non-negative integer. I almost did it. When we get to it, you'll see what I left open. It's kind of amusing. Overwhelmingly, I did it, but I failed to cover all cases. There's still some elusive cases. All right, and then this one is all the remaining ones. This is all the remaining ones. When I have right parentheses, and this means it could be either one. And the star means it's extended real number. Extended real number. If I don't have a star on it, it means it's a real number. All right. So I completely solved these. They're all usable. They're all good. And these are a few of them are good and most of them are bad, but some of them are open. Some of them are open. All right. Now I've been playing around with this, and I don't like the idea that there's nothing in here like that. It's just that I never was happy with what I did do this along these lines. But I'm going to put something in there. By hook or by crook, I'm going to do something in there. I mean, I already know some things, but I'd like to make them stronger. And so this is something that I am going to add and probably tell you about next. I'll definitely tell you about next week. Certainly, I'm going to tell you if I've solved this completely. And then this is just cleanup. This is an easy proof that the statement that's reversed in chapter, I think it's 6 now, in that old reversal section, this is a statement that's reversed in the old uh, reversal section. Actually, it was reversed even the weaker statement, where these are k, the same as the dimension. We want to do is prove that all the statements here, except that one that I don't understand, easily implies this. So this reverses all the statements here, except that one. What is that one? You see, I said almost. Where is it? Almost all statements. So the one that I don't understand is when you just do it on Q, and that's for a maximal invariant maximal chain. If you do the initialization form, yes, I know that that's strong. And if you use the interval form minus n, then I know that's strong. But this statement with just Q, I screwed up on that enough times that I dropped it. Of course, I'm going to go back to that at some point, but I don't have it. I don't have it. All right. So remind you of the lead statement of the subject. Every ordered invariant relation on every minus n k has an n-shift invariant maximal chain. The next section involves emulators. And we show that all these four statements are equivalent, and this is the initialization form, which is the strongest one. Oh, this is the one. This is the one. This is the one I don't know the answer. This is the one that's open. What the status is? Yeah, this is the one. But this is the initialization one, which is stronger than the one I don't know. This is the initialization one, where there's a uniformity in here, where the n-shift and n-equivalent invariant maximal chains are uniformly obtained from S by restriction. And then I have that all these things are the same. Yeah. Okay, go ahead. I'm just on the phone into Europe. All right. So here we have the state. We do a circular implication. In other words, this applies, this applies, this applies, this applies, this implies this. So they're all equivalent. So we do that. Nothing new. Well, no, this is new. This was reworked. There was some little bugs in the way I set it up before. Yeah. So that's been redone a little bit. This hasn't been changed. And sort of anybody would expect that any of these statements I look at, if they're true in dimension k plus one, they're automatically true in dimension k by adding a kind of dummy variable, as you might expect that. That's easy. All right, now this is here are the proofs we do want to talk about. This is new. This one's not new. This has been around for a long time. To prove the statement for n equals 1, you just list all the invariant relations. There's only 8 of them. There's only 8 of them, and then you look at who are the maximal chains in the initial segments. They're all just the singletons. Remember, chain means any two distinct elements are related. So you get singletons as maximal chains a lot. But then here, when you have everything, of course, those are the maximal chains. These are the unique maximal chains. These are not unique. Okay, and then you immediately get the statement is proved because you can take a singleton, and you can take singleton minus 1. Singleton minus 1 is very invariant. Singleton minus 1. All right. Now, proof using omega 1. So we do it in 4 stages, and we fix an order invariant relation R on Q squared. Now, this is the W that we need. It looks a little strange. It's W1 cross the rational interval, left open, right closed, left closed, right open, rationals. But we throw out the point 0, 0. I'll tell you why in a second. And then we add this point at the top, omega 1, 0. We add this ultimate point at the top, and we put 3 orderings on. So the reason we want to throw out 0, 0 is because eventually we want this to have no left endpoint. Remember, we're trying to prove a statement involving Q. We're trying to prove a statement involving Q, namely this initialization form of invariant maximality, which implies all the other forms of invariant maximality. And remember, this is a positive result, so the stronger the statement, the better, so to speak. Okay, so this would be this would be the left endpoint if we didn't throw it out. So we want to just throw this point out so that it's no longer has a left endpoint. No big deal. And then we want to have we do want to have the right endpoint for technical reasons of the way this proof works. Because omega 1 is going to be cut back into various limit ordinals, cut back into various limit ordinals. Okay, so we fix an effective linear ordering. I mean, we've seen this kind of thing before, but this is the final kind of version of it for the book. For this part of the book, the local stuff is similar, but there are stronger theorems about varying the local finite or map, one-dimensional finite map. So there's some more stuff there. Do you have any questions for me?
No.
And you'll put the linen and stuff in the washer. I can start the washer, but you'll put it in the washer.
Okay.
Yeah,
Yeah.
just put them in there.
Okay.
Yeah.
Do you have any clean sheets for?
Yeah.
Okay.
There's a bin. There's a bin right against the wall
Okay.
in that
Get
room.
something.
It has
Okay.
everything and only that.
Okay.
Okay.
All right. Thank you.
Yeah. All right. So let's see. So okay, but then we do want a so-called first point. We do want we definitely want a left endpoint for one of the other orderings. Actually, I never called it that, I think. That. There we go. And we just take a half to be the first point. Okay. So omega 1 is the first uncountable cardinal. OW is this. Okay, so all this. Now, less than star is the lexicographic ordering on pairs. And less than double star, this is this well ordering. This is what the other thing is a dense linear ordering with only the right endpoint, no left endpoint. This one is the linear ordering double star given by this is a well ordering. First order by alpha and beta, the first term, and secondly order by I'm sorry. Less than prime was meant for another purpose. Just a second here. Let me get this straight. There's a linear ordering on zero. There's an ordering on 0, 1 that's of type omega. Now, where did I put that? Here we are. I'm sorry, that's prime. That was right. That was right. Sorry. That ordering is just a special ordering of type omega. The first two elements are 0.5. Yeah, first two elements are 0.5. And we're going to throw out 0 right at the beginning. So half is the first, but ordinarily 0 and then a half. Okay. And then double star is your first order by the ordinal, and then you order by this this ordering here. Okay. And then that's a well ordering, and then this is another well ordering. This is the well ordering on omega squared, which is the lexicographic. I forget what it's called. The lex max. So you order first by the max, and then you order lexicographically within the same max, order lexicographically. All right, and these are the reflexive closures, so the equal just means that. Okay. And then when we go do this for an arbitrary kappa, it's essentially the same definition exactly. Except instead of 2, there's a K here. Okay. Note that for W, we've thrown away 0, 0, so that less than star has no left endpoint. However, double less than star and double less than double star and less than double star 2 have left endpoints. All right, so here we have less than star is dense with no left endpoint, and right endpoint omega 1, 0. Less than double star is a well ordering on W with left endpoint 0, 1/2, and right endpoint omega 1, 0. And this set here is the set of limit points of W. Right. And this is a well ordering on W squared with left endpoint 0, 1/2, 0, 1/2, and right endpoint omega 1, 0, comma omega 1, 0. Okay. Now for alpha less than or equal to omega 1, we chop it down to omega W of alpha square bracket, which is alpha cross 0, 1 minus 0, 0. We got to throw that out again. Together with alpha 0 is the top point. And so W itself is just W of omega 1. Now we transfer notions from Q less than to Q less than star, culminating in the definition of R star. Remember, R was the given order invariant relation on Q to the K, on Q squared. So 2 elements of W to the 4th are order equivalent, less than star order equivalent, if and only if xi less than star xj, if and only if yi less than star yj. T, a set T is invariant. These are just the obvious definitions you'd make. And less than star order invariant relation on W star is a relation on W star such that its graph is an order invariant relation, order invariant subset of W's to the 4th with respect to less than star. Now, to orient oneself, the most important relation in some sense is less than star, because that's what's going to become less than on Q. Less than star is going to become less than on Q. Well, less than on Q with the right endpoint thrown away. Yeah, with the right endpoint thrown away. It's going to be less than on Q. The less than double star and less than double star 2 are just auxiliary well orderings needed in order to make a transfinite construction. Less than star, this is the most important. Less than double star and less than double star 2 are used in order to support a transfinite construction. Okay, that's what is going on. Now, finally, R star, which is the extension of R, which is the transfinite form of the given order invariant relation on Q, is just what you'd expect. It's the canonical lifting from Q squared to W squared. We start with an order invariant relation R on Q squared. Now we get an order invariant. Now we get a star less than star order invariant relation R star on W squared, right? Okay. Yeah, this just says that the definition is what it's supposed to be. All right. The second, okay, so the first stage in these proofs, they're all, uniform proof. First stage of these proofs is the setup of the orderings. It's just the setup of the orderings and the relation. It's just setup stuff. Now we do the crucial inductive, in the recursion, transfinite recursion. So we build an inductive chain in R squared. It's going to be a maximal chain, but it's not just any old one. It's the canonical one. It's the inductive one. Okay, so it's a subset of W squared, and it's defined as follows. X in W squared lies in ICH R squared. Inductive chain. ICH means inductive chain. Lies in the inductive chain if and only if the set of all y less than or equal to x that's in this thing up to now, is a chain in R squared, in R star. I didn't say, yeah, this is not quite right. What I meant to say is this. Yeah, this needs to be fixed. Union singleton X. Yeah. Okay, I should fix that. Yeah. Yeah. So you put X in if and only when you take all the stuff that you've already put in before X, smaller than X. If you do that, then and you put X on, it's still a chain. And of course, this is screwed up too. This should be 2. Because we're ordering pairs from W, not just elements of W. We only did less than double star mainly in order to give the definition of less than double star 2. In order to get that definition done, we need first the definition of less than double star. Yeah, okay, now I think that fixed this. So now you have the usual thing. This is a chain. And if you're outside this chain, there's somebody smaller. Yeah, I think this is. There's somebody smaller in the chain such that it's not a chain with X. So it's not a chain with X in R star. Yeah. Okay. For all alpha less than or equal to omega 1. Yeah. So for all alpha less than or equal to omega 1, ICH of R star intersect W alpha is a maximal chain in R star restricted to W alpha. I may actually want to state this stronger because I think it comes up. When you restrict this to all the things smaller than a point, not just inside a big hunk like this, and in fact, this should be like this. Restriction is fine, yeah. You get maximal chains. You're always getting maximal chains, no matter how up you go. Maximal chains in the section in which you're working. Yeah, this is probably stated a little weaker than I want to state it. Just 1 second. Can you turn this down some? Because I'm on the phone in the. Can you turn this down?
Hey.
Oh,
Oh, my mom, yeah, I said.
oh, I didn't know there were 2 people. Okay, but I'm on a phone here.
Okay, yeah, I turned it down.
Okay.
Oh, that's all right.
Yeah, I thought you were the only one here.
Oh, no.
All right. Okay, so okay, so that's the section about the inductive chain and how good it is. Now, we start to really get into this. We need a combinatorial study of this chain. All right, so we have to do first. We do a thing that I still use logic for. I think it can be easily removed, the logic here, but I don't think it's worth it, and I certainly don't feel like it. So you see a little bit of logic here. So we find a closed unbounded set of countable ordinals that interacts in an important way with ICH of R star. To do this, we argue model theoretically, starting with a structure. So we start with this structure. We put the two orderings in here. The thing with the two is just defined from here, so it's not really important to add that. All right, so we have the constant here, and we have this is a predicate as a predicate. Yes, well, yeah, but it's a binary relation on W. It's a subset of W squared. All right. There's a closed unbounded set E such that the structures, when you restrict, so I'm just using this to mean general restriction whenever I'm in a structure. I'm going to restrict to the domain. Restrict to the domain. By the way, this is not quite W alpha. It has an omega 1 there, right? Okay, these structures here are elementary substructures of this, right? In other words, we take this big structure here. This is the one we start with, and we want to find countable elementary substructures of this. A tower of them, closed unbounded tower of them, of elementary substructures. And this is, obviously we're going to keep the same constant here because they're elementary substructures, so this has to be the same. But it's this fill in the gap thing that's done a lot in classical model theory, that you can do this, and that you will get a full-blown thing here, with nothing else. Full-blown thing here with nothing else. And you use omega 1 as regular heavily, of course, to do this. It's all standard classical model theoretic thing. And that's closed unbounded, and that's E. That's very important. Now, given alpha and E, if you take this structure, this is isomorphic to a structure where this omega 1 0 becomes alpha 0. See, and this becomes a W alpha because we're throwing this away. We're replacing this with this. And I write suggestively S alpha. I don't want to put too many symbols in this thing, you can't read it. Where S alpha is our chain restricted to W alpha. Okay? This is sort of like the Gödel transitive collapse or whatever you call it, but it's a very special case of it. See, the isomorphism we're going to get is just maps, is the identity below alpha, below alpha, so to speak, meaning alpha across this, the identity below alpha and maps omega 1 to alpha. See, omega 1 0 actually to alpha 0. The structures have all this pairing going on axiomatically, rudimentarily, without adding any pairing functions in here. It's not like that, right? Because the domain is a set of pairs, right? Okay, so we write this structure as W alpha with these things restricted, and alpha comma 0 instead of omega 1 0, and ICH R star restricted. But how do I know that S alpha is actually ICH R star restricted? That's not clear. And that's proved because this structure is an elementary substructure of our master structure, and our master structure satisfies ICH-R stars defined inductively. The inductive definition is a sentence, and that sentence has to be preserved, so that sentence is true in here, and therefore that sentence is true in here. But the only but since we have well-foundedness, if you're going to satisfy that sentence that this is the satisfies the inductive clauses, and that's a real transformative recursion. That's the real one, and therefore this has to be just has to be this. You see. So that's how you prove that this S alpha is just the restriction of ICH of R star. It's just a restriction. All right, so let alpha be less than or equal to beta from E. This just consolidates this in the special case of pairs here. And X is less than star alpha 0, then X alpha 0 is a member of inductive chain if and only if X beta 0 is a member of the inductive chain. Because the isomorphism here is the identity on these alpha zeros and beta zeros. It's the identity, and it just maps. Yeah, it's just the identity, and it maps. Yeah, it maps alpha to omega 1. You get an elementary equivalence between alpha with omega 1 and beta with omega 1. And since omega 1 and omega 1 are the same on both sides, you get alpha and beta are equivalent. So that's why you get that. Okay. See, this is the kind of large cardinal combinatorics that you want to do. This is what you want to do. This is the combinatorial thing you want to do when it's two dimensions. All right, but there's another problem. We also want to see this is very much like the n shift equivalence that we're talking about, or n equivalent invariance that we're talking about that we want. But n equivalent invariance also includes the case where both things are both are indiscernibles. And that has to be done separately, but it can't even be done. You have to actually reduce E. E prime consists of infinitely many elements from the first omega elements of E, so that this does happen. And then you do this by brute force using brute force application of Ramsey's theorem, the infinite Ramsey theorem, the omega Ramsey theorem, for four tuples, I think. Yeah. So you just use the Ramsey theorem to get this. Okay, so now we're in really good shape. We know that with this E prime that we know that we have a lot of regularity here in membership in ICHR star. So what we do is we just add some notation. So lambda naught, lambda 1 lists the first omega elements of E prime. You can easily prove that these are, going back here, that these are limit ordinals, actually. All right, lambda is the omega element of E star. Remember, it's closed unbounded, so lambda is just a soup. And W lambda is just W without lambda 0. That's not what I mean. Okay. This is what I mean. No. Oh, maybe I can't do that. Just a second. Just a second. There we are. There we are. Okay, and M is this structure now, where we have these constants. This is a structure we want to consider. Now recall the definition of n equivalent on Q squared and n equivalent invariant for subsets of Q squared. We now transfer these in the most obvious way to the transfinite setup. This is just the most obvious shifting of context. And so we get that the equivalence we're talking about it can be done explicitly because this is only two dimensions. It's pretty clear what the definition of when these things are equivalent with respect to this omega sequence of ordinals. And then we see that we have the equivalent invariance. We definitely have the equivalent invariance that we want in here. See, we definitely have it. If these things are equivalent, then they must be related in the obvious way. These pairs must be related in the obvious way. This shouldn't be I. This should be lambda sub I. Yeah, that's not okay. There we are. Yeah, this should probably be W sub lambda I think. Yeah. All right, there's a little cleanup here because I want to throw away the top point. Yeah, I may want to introduce a notation for when I take W of alpha and I throw away the top point, alpha 0, in order to make this clearer. But this is just a minor point. All right, so now that we have that this structure is so good, in other words, these things act like indiscernibles for this. These things act like indiscernibles for this. And I actually do have maximal chains. When I restrict, I get maximal chains. That goes back to that much earlier thing. Remember when you take ICH R star and you cut it down, it's a maximal chain, the stuff that you cut down. Yeah. All right. So we've got a very, very good structure here. Now, unfortunately, it's uncountable. But now what do we do with it? Well, we take a countable elementary substructure of it. We take a countable elementary substructure of this thing. And then this structure, this countable elementary substructure has the invariance. It inherits the invariance because that's first order. So we still have this invariance. And we still have this maximal chain condition. We still have the maximal chain condition. I'll probably put a minus here or something. I'll fix that for next time. Anyways, I'll fix that in the final version. And so we have the maximal chain stuff, and we still have the invariant stuff. Just because we take a countable elementary substructure, we still have that stuff. But now that it's countable, we can make an isomorphism onto a countable version. In other words, it'll be Q less than some S 0, 1, dot, 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 where every S restricted to less than or equal to n is a maximal chain, and R star restricted to less than or equal to n, and S is an n equivalent is n equivalence invariant. And that's exactly what we aim to prove. That's exactly what this statement says. Okay. So this is something that doesn't have any large cardinal combinatorics in it, and is a kind of doable in a colloquium in a math department, almost doable, doable to almost doable if you're careful. And it's a theorem of ZFC because all you did is use omega 1. Now, with an SRP cardinal, we do the same thing. Everything's the same until we get to that point where we're talking about equivalent invariance. It's all the same. Inductive chain's all the same, except I'm going to have to debug it like I did this other thing, like that. And here's where the equivalent invariance has to be verified, and there you need the large cardinal, namely k minus 2 subtle. So all this is the same. Yeah, I don't want to go into too much more detail. I just eat up all the time, and I wanted to get to something else. But anyways, you do have to do the large cardinal combinatorics with a little bit of a pain. Uh, all right, you can see this in the final version. Anyways, this was done many times in the last many years in one form or another. This is my official, because I want to link it so well to the Mega 1 case. Uh, and we get to the same place. We have this in the maximal chain in the same good-looking structure that we had before, except now the dimension is k. Yeah, it's going to help a lot to introduce one little piece of additional notation. When you throw the tops out of these initial segments of the construction. Yeah, it'll help debug this. All right, it's no big deal. So, the same thing. Exactly. So I try to make this proof the same thing, except there's one sort of big spot where there's large cardinal combinatorics going on. And then now, if k is fixed, you can just use a k minus 2 cell. So instead of starting with an SRP cardinal and then fixing k, we can first fix k and start with a k minus 2 subtle cardinal and proceed without any change. Because we already showed the k minus 2 subtle was enough. All right, this is the section about formalizations, where we claim that these things are implicitly positive or 1 because we develop a sentence in first order predicate calculus whose validity is equivalent to the statement in question. And that goes back quite a while. I do that in some detail here. Yeah, that's enough. That's all right. All right. This is all right. This is all technical stuff. I want to get to one last thing. which is more exciting, a little bit more exciting. Here, we want to know what intervals this invariant maximality works on. So far, all we know is minus n, comma, n closed. So we look at intervals of this form with, I mentioned this earlier, with extended real number endpoints, extended real number endpoints. And we always have to worry about whether it's talking about open or, is it left parenthesis or left brackets, right? Of course, it's never left brackets when it's minus infinity, and never right brackets when it's plus infinity. That goes without saying. Okay. All right, so here's what we're looking at. We're looking at this where J is now a parameter. We want to know when this is true for which J. And the statement, as always, is universally quantifies over K. So in the original lead statements, J is minus n, comma, n closed. So we call it secured if it is n shift secured if and only if it holds with n shift, and equivalent secured if and only if it holds with it with n equivalence, with n equivalent invariance. It's secured if it's both, but if it's n equivalent, it's secured, it's obviously secured, because n equivalent secured obviously implies n shifted secured. All right. Well, this tells me what I'm going to do. Might as well just do it. So there's some lemmas about if you know that one of these things is secured, if you know that one interval is secured, then you know another interval is secured if the two intervals are closely related. So there's a couple of lemmas like that make things easier. Then in this section, we look at the case where it starts with left bracket n, where n is a non-negative integer. This is the case that there's something I don't understand yet, but I did this. First, I did this case. If this interval is contained in n plus 2, right open, then you can actually see, I mean, I actually thought I might have enough time to do this kind of thing today, but I don't. The n shift equivalence and the n equivalent invariance and the n shift invariance are very, very limited, because you're talking about just moving one indiscernible to a higher one. The only way you could do that is to move n to n plus 1. You can't move anything to n plus 2 because it's not around. But only moving n to n plus 1, it's only legal if n is the max. And so you're only talking about moving n through n to n plus 1 through n plus 1. And you can actually make sure that you can do that in RCA naught. There's no real bite that's in that. Okay. Now, if m is big, if m is at least n plus 2, and we're including it, then I have a way of showing this is not. Oh, I didn't say this. Yeah. Now, if it's n to infinity, that's a whole different kettle of fish. If you go from n to infinity, that I've been able to show is not secured. That's really bad. N infinity is really bad. And it's important that that be N, not some rational, not some real number, it's important that that's a non-negative integer there. And then I'm able to do it even when I just assume that M is at least N plus 2. And I can do it with X as long as N plus 3 is in the interval from N to X. But there's this intermediate case where N to N plus 2 closed is properly contained in J, is contained in N to N plus 3 open. And that one I didn't see how to answer yet. I think this is a doable problem, but it may be tricky. So I don't see this yet. Maybe I should be able to do this, but not right away. So besides that, I know everything because the remaining intervals, for example, whenever this is a left open, this is a left parenthesis, that this is fine. This is secured. And this is all right with the left brackets is all right if X is not a non-negative integer, that's also all right. So I know almost everything there. Okay, so this is something I definitely want to put I want to put something in here. I need to put something in here, and I don't know what exactly yet. And this is the cleanup that links me to all the reversals. So I don't know why this is going on. So, oh yeah, I had to explain what this thing is that's reversed in that chapter 6. I just took the definitions. It's graphs and so forth. So the reversal in it's not chapter 4, it's 6, right? That's that reversal. And now we link it to everything in this. We link it to this chapter. So we're able to show this is pretty easy, actually. We're able to show that this implies this. One thing that we do is multiply through by n. Well, I don't know how I set it up. Maybe I divide by n in this statement, and then I prove this statement when I divide this by n. Yeah. All right. This was a bigger slog than I thought it would be, but this is the last lecture on this chapter, maybe with a little bit of additional discussion next time. Okay, I'm done now.